Hi and welcome to the video of implementing RAG with Cosmos DB and Azure Foundry. First of all, let's see what kind of problems we are going to solve. An LLM only knows what's in its context window. Ask a model about your product catalog, your internal docs, or last week's support ticket. And it has nothing to go on unless you put that information in front of it. RAG solves this by retrieving the most relevant chunks of your own data at query time and feeding them into the prompt alongside the question. The retrieval step depends on semantic similarity, not keyword matching. That means turning text into embeddings, high-dimensional vectors where meaning translates into geometric closeness, and then finding the nearest neighbors to a query vector fast, at a scale without a full table scan. The actual engineering question might be, it's not how embedding work, but that part is a single API call. It's where do I store millions of vectors so I can find the closest ones in milliseconds, while still filtering on category, tenants, price range, or permissions. That's a database problem, and it's why the store you pick matters. Okay, let's see why put vectors in Cosmos DB instead of a dedicated vector database. You don't strictly need a separate vector database. If your operational data, products, documents, support tickets already live in Cosmos DB, you can store the embeddings just as another field on the same document. Here is what that buys you. One store, not two. The vector lives on the same document as the data it describes. No sync pipeline keeping a vector DB and your source of truth store consistent. No drift, no dual writes. Native filtering, not bolt-on. A single query combines a where clause with a vector similarity function. Filters are applied at a part of the same execution, not a post-hook re-rank on the client. Okay, global distribution. Turnkey multi-region replication means low latency reads for RAG queries wherever your users are, with the same tunable consistency model as the rest of your data. We can use manage identities with no keys. Default Azure credential covers both the data plane vector query and the embedding call to Azure AI Foundry. Nothing to rotate, nothing to leak. DiskANN at scale. Microsoft disk-based approximate nearest neighbor index handles large vector counts with high recall and sub-linear query cost without holding the entire index in memory. Change feed re-embedding. React to document updates automatically and regenerate embeddings only when content meaningfully changed. No separate pooling job to maintain. Okay, let's see when Cosmos DB might be a wrong choice. If you need pure vector search at very high recall over hundreds of millions of vectors with no associated operational data, or if the rest of your stack has zero footprint in Cosmos DB already, a dedicated vector database or Azure AI search may be a simpler fit. Okay, let's explore vector indexing. What DiskANN actually buys you. Cosmos DB's NoSQL API supports 3 vector index types on the container's vector policy. They trade off build time, memory footprint, and recall differently. Worth knowing which one you are picking and why. Flat exact search. Brute force scan, 100% recall, simple but capped at roughly 10k vectors per physical partition. Fine for small catalogs, not for production scale. Quantized flat, compressed exactish. Quantize vectors to reduce storage and improve query speed while keeping accuracy close to exact search. A reasonable middle ground for mid-sized dataset. DiskANN. Approximate scales far. Microsoft's own disk-based and algorithm, high recall at large scale without loading the full index into memory. the default choice for anything production sized. Distance functions, 3 options, cousin, dot product, and Euclidean. For OpenAI Azure AI Foundry embedding models, cousin is the standard choice. The models are trained so that direction, not magnitude, carries the semantic signal. Dimension limits. Vector indexes support up to 4096 dimensions per property. Text embedding 3 small at 1536 dimensions comfortably fits. Worth flagging it if you ever consider the 3 large model or a custom trained embedding model with a large output size. Let's explore filtering, the part people underestimate. This is arguably the biggest practical reason to reach for Cosmos DB over a pure vector store. Filtering is bolted on after the similarity search runs. It's part of the same query that engine optimizes. Pre-filtering vs post-filtering. With many standalone vector databases, you either filter after retrieving the top k nearest neighbors. Post-filtering, you can silently lose relevant result if they weren't in the same initial top k, or you rely on store-owned hybrid mechanism, which varies widely in quality between products. Cosmos DB applies the where clause as a real filtering during query execution. So a category or tenant restriction narrows the candidates set the vector search actually considered. As you can see in the select statement below, we are selecting over a product catalog, and inside the where clause, we are filtering the query with category of the products at the same times where we are searching for similarity. Okay, let's see what we are going to build today. We will have a product catalog application which contains a function application, and this function application has 3 endpoints. One of the endpoints is seeding the database, in our case Cosmos DB. And when we call this function, it will use Azure Foundry to create the embeddings as well and seed the database with 20 clothing products. And then after that, we are going to see how we can search our Cosmos store with similarity search. After that, I'm going to show you how you can update an existing product, but only update the semantic and embeddings when the meaning of the description or title of the product has changed, and we are going to do that with the change feed of Cosmos DB, so you are also going to learn that. So without any wasting time, let's dive in. Okay, here I am at JetBrains Rider, and I am going to show you what we have in our code base and solution. So inside our solution, there is a folder which is called Bicep, and in this folder I created some biceps files with a readme about how you are going to deploy these resources in Azure if you want to follow along. Okay, first we are going to deploy our function app with function flex bicep file, which I'm going to show you in a minute. Alongside, we will have a storage account relating to the Azure function, and also we are going to enable the system managed identity of this function. Then we are going to provision our Cosmos DB. Here we create a database there called catalog, and inside that we will have a container called products, and we are going to partition the product container with category field. The vector embedding policy tells Cosmos DB that this container has vector data and where to find it. In this file, it is pointing at the embedding field. This one, and the dimension, the length of each embedding vector. 1536 means every value at embedding must be 1536 number vector. The distance function, the similarity metric used when comparing vectors. COSIN means Cosmos DB ranks vectors by angular similarity, which is the common choice for text embeddings. Indexing policy configures how Cosmos DB indexes fields in the container. Here it includes a vector index for embedding. I mean the embedding fields. And the type is DiskANN. The vector index type being used is the vector indexing approach Cosmos DB integrates for approximate nearest neighbor search with low latency and good scalability, which we had talked about it earlier. After that, we are going to deploy our Foundry, which is going to use text embedding tree, a small model for the embeddings. And then we are assigning the roles for our access to the Cosmos DB. So by this role, our Azure function will get data plane contributor role to access Cosmos DB. And also we are going to have another role assignments that I'm going to show you in the portal if you would like to know how to do it there. So let's go and see what we have in the code. I'm going to open the solution and close down these files. Let's see first what we have in our product inside the models folder. This product is going to hold our data in the database. In the products container, we will have an ID as usual, the category, which is our partition key, the title of the product, description, price, embedding, which holds our vector, and also we have content hash, which is the SHA 256 of title and description at the time embedding was last generated. So we are going to compare it in the change feed if this value has changed. If yes, then we are going to regenerate the embeddings. And also we have here a product catalog, which is our 20 dummy products that we are going to seed in the database. And speaking of that, we have here seed endpoint product. And if we go down, we can see that this is an HTTP trigger function, and it just iterates through the static product catalog, and it just create the embedding input here with the combination of the title and the description of the product, and calls our model, and then also create the content hash as we described, and insert this product to the database each by each. Okay, I'm going to open up our search product function, which is an HTTP trigger, and here we are getting our query from the query string, and if we have any value provided, we are going to continue and call our embedding model, and basically trying to create the query based on that with the built-in vector instance function, and then running our query and returning the results to the user. The next function is the update product, which is simply just again an HTTP trigger with the put method, and it just updates the product. And after the update and mutation happened, a change feed will basically gets triggered. This function has an payload, which is update product request. It has a nullable title, description, and price. And if we now check out the product change feed trigger, here we are going to see that our Cosmos DB trigger is also using the product lease container for storing the checkpoints, and also it is reacting to the products container in the catalog database. And in this function, we are going through the changed product in a for loop, and we are basically create an embedding input and hash them, and then compare them with an existing product hash content. If they were equal, so we are not going to do anything. So we are not going to basically create the embeddings again, in the case that we just only updated the price in our example. But if the similarity was not equal, then we are going to generate and save it to the database. In our program class, we are going to register Cosmos DB client to our dependency injection, and we are going to use default Azure credentials to be able to assign manage identities. Okay, I'm logged in Azure, and I have here a resource group which is called RG-RAG, and we are going to deploy our necessary and needed resources one by one. So let's get into that. Let's get back to Rider and close all of these files. I switch to the file system, and I'm going to run the function flex bicep. So I'm going to open the README section, and we can basically copy this command from here, and then open our command prompt, and paste it here. Press enter, and we will wait until our function app is created inside our RG-RAG resource group. Okay, the deployment is finished. I'm going to open the portal and refresh this page. And as you can see, we have our Azure function, our application insight, and our app service plan, and plus the storage accounts are deployed here. Next, I'm going to deploy our Foundry. So from here, again, we copy this command and paste it here and wait for the deployment. Okay, our Foundry service is created. Let's check the portal, refresh here, and we see that we have our Foundry service deployed. Let's go back to Rider and deploy the Cosmos DB. I copy the code and paste it in the terminal and wait for the deployment. Okay, our Cosmos DB is deployed. We can check in the portal. I refresh again here, and we have our Cosmos DB deployed. So let's go back to Rider and deploy the role assignment. I have here a script which I'm going to paste it in the terminal, but for this one we need two parameters: the principal ID of our Azure functions, which I'm going to show you from where you can find it. So if we open Azure Functions, here under setting identity, you can copy this value and go back to Rider, and we just paste it here. And also we need the name of our Cosmos DB, which I'm going to paste it also in the line above. Then we should be able to move forward and press enter. Okay, our role assignment is done successfully. And now our Azure function is able to access Cosmos DB only with the actual URL of the Cosmos DB and not the key or any kind of secrets is stored in the application code or configuration with the help of managed identity of Microsoft Azure. Okay, our Azure function also needs to access the Azure Foundry, and for that we are going to also provision another role assignment. If we go to the Foundry service, from access control, I add here a new role assignment so you are able to see how you can do it in the portal. And I'm going to search for Cognitive Services User role. This one, and click next. From this page, from this tab, I'm going to click on Manage Identity and then select Members. Here we are going to find our Azure function and select. And we are going to assign this role to our Azure function. Okay, with that in place, our Azure function should be successfully connect to Azure Foundry. And the next step is that I'm going to open Rider and deploy our application to Azure Functions. Let's close this page and also the terminal. I go to the solution folder. Right click on the project and publish to Azure. I pause the video until the deployment is done. Function application is deployed, and you can see our 4 functions are here in the list. And if we go to environment variables, we need to add 2 new environment variable, Cosmos endpoint, where you can find this value in the Cosmos DB and inside the keys menu. This URL is the value that we need to put to the environment variable of Cosmos DB endpoint, and also we need one for Foundry endpoints, where we can find it also in the keys and endpoint section, which is this value. So after that, without any storing keys and secrets, we should be able to call these services from Azure Functions. Okay, let's go and fire an HTTP request to the seed function to see if we are going to seed the Cosmos database. So I am here in Insomnia and I have 4 endpoints which I'm going to call. I'm going to first call the seed endpoint to seed the database. Let's try this out. And as you can see, successfully we inserted 20 records to the database. We can go and check it out. Okay, let's go to Data Explorer. And under Catalog DB, we click on the Products container, Items, and we are able to see our seed data is here, and we have our embedding field, price, description, title, category, and ID. And next is to see if we are able to search something on this data. So let's open Insomnia, and I will click on the search. And here I have a sentence like, I would like to buy something to protect my face from the sun. So this is something that basically our search is going to find by the meaning. So I will try to send this request and see what is the suggestion of our embeddings. So it returned the product with ID 3, canvas baseball cap, which is a basically perfect fit for protecting your face against the sun. So we did this search without mentioning any cap or a specific title or description of the product. Let's search, for example, for something else like comfortable sports shoe. Let's see what we get now. We get, for example, retro leather sneakers, comfortable low top sneakers, and this is what is suggested. We can also try by another search. Let's try this one. I would like to buy a jacket that is stylish for work. And we send it. A wool business overcoat, formal wool overcoat with a wind restriction, a smart winter outwear for the office, and so on. Let's try, for example, another search term. I need a 100% rainproof jacket and see what we get. We got product 18, hooded PVC raincoat, which is fully waterproof PVC raincoat with the attached hood. So these are the suggestions that meaningfully is returning by the semantic search. Now I'm going to update the price of the product, and our Cosmos DB change feed trigger should work, and it should detect that there was no change in the title and description. So it needs to basically skip the embeddings. And I'm going to click on update price, and basically here I'm going to update the footwear, which is the category of our product, and the ID is 16. So I'm just going to update to, I don't know, for example, 160 and see the result. Meantime, we can go to the logs and see what we get here. Probably we need to repeat this step. Anyway, the update happened. It is 160, but I'm going to change it to 150 and try it again, because we would like to see the logs. As we can see here, it is stating that our product change feed function is triggered, and we skipped the re-embedding because it was detected that we don't need to re-embed, because as you remember in the code, the hash content is compared and there is no change in the title and description. The next step is that I'm going to update the title and description of the product, and we are going to search again and see if our change feed trigger is successfully re-embedding. Let's click on the update description, and we are going to change the title to iSphere wool socks, and the description: these socks are great for cold weather and keep your feet dry during hiking. I will send this request, and I have also the logs open so we can go and check it out. But anyway, you can see that the title and the description is changed. We can check the logs. If we open the function in the logs, we can see that the re-embedding 16 after content changed. So this log is coming from the code base, and it shows that the trigger was successfully re-embedding. Okay, now we can search and find out what it will come out from the semantic search results. go back to Insomnia and I open the search on the params. And here, for example, I search for, I need a breathable socks for my trip to Iceland. Let's see what we get back. We got product 16, iSphere wool socks, exactly what we changed. And this brings us to the end of the video. And I do hope that you enjoyed the video and hope to see you next time. Until then, take care. Bye.